Welcome to the video lesson for section 9.7, polar graphs. We're going to go ahead and explore different types of equations and graphs for polar functions, and then we're going to talk about some features and how to identify specific things. Let's go ahead and get started. The first polar function we'll be discussing is a limosome. And for our limosome, we have two different types of equations. We have a plus or minus b cosine of theta, or a plus or minus b sine of theta. So for this equation, your a and your b are going to be constants, and then your theta is going to be your variable. And if we were trying to graph this, we'd be plugging values into our theta function to get our ordered pairs. When you look at your graph, you can see we have what is kind of like a heart-shaped function. And this one would be the cosine version because it is what was called more of a horizontal limosome. If we were to take this and rotate it 90 degrees and have it facing upward, it would then be our sine version. Our next polar function is the rose curve. And a rose curve got its name because when we look at the graph, we see that the function actually has different petals. The type of petals, or actually I should say the number of petals, is directly related off of what your n value is. If our n value in our formula is even, then you actually have 2 times as many petals. So if my n value is 2, I would have 4 petals. If my n value is odd, then I would have exactly that many petals. So if I had an n value of 3, I would see 3 petals. For the cosine versus sine function, it differentiates the type of symmetry we have, which we'll talk about later in the chapter. We also have a circle. And for your circle, we have vertical versus horizontal circles. For our cosine function here, we would have the horizontal one because you're going to be moving in your x direction, and the actual diameter of your circle would end up being a. For the vertical one, this would be your sine graph, and again, your diameter would still be a. For our next and final type of graph, we have a lemniscat. And for our lemniscat, it basically looks like an infinity sign, which is kind of a cool function. It's actually one of my favorites. What we see here is actually an example of the cosine function, because it's more of our horizontal version. If we instead had a sine function, you would see this would be rotated slightly, and we'd have some different types of symmetry going on there. For each one of our functions, we have a few things we want to be able to identify. First off, looking at either the equation or the graph, you want to be able to identify what type of graph that you have. Once you have the function graph, we want to look for types of symmetry, and there are 3 different types of symmetry we can find. We also want to be able to identify maximum values and discuss the zeros or the intercepts for your functions. Let's go ahead and look at some graphs and identify some of these things. When we're discussing polar functions, we have 3 main types of symmetry we can discuss. The first type of symmetry is going to be the line theta is equal to pi over 2. And you can think of this as your y-axis. To verify that something has symmetry with theta equals pi over 2, we can kind of go back to what we did for even and or odd functions. If we have a point r comma theta, instead of x and y, we have r and theta for your polar functions, and you replaced it with negative r and negative theta, you would get the exact same point. So again, you have symmetry across the y-axis, or the line theta is equal to pi over 2. If you take a point, replace it with the negative values, and you get the exact same point. Our second type of symmetry is going to be the polar axis, and this is essentially like your x-axis. So for this type of symmetry, if you have a point r comma theta, and you replace it with a point r negative theta, again, you end up with the exact same point. And again, this would be symmetry across your x-axis, so to speak. And then last but not least, we have the pole, which is the origin. And something has symmetry across the pole if you take your points, r comma theta, and you replace it with a point negative r theta, and you end up getting, again, the exact same point. So we're going to go ahead and look at some graphs here and discuss which one of these symmetries they have and how we can determine that. All right, we have in front of us a limosome, and I've drawn in our 3 axes of symmetry. For theta equals pi over 2, that was our vertical line, or kind of like your y-axis, so we can see that going here. And then for your polar axis, that was your x-axis, or the horizontal line, so this yellow one going across here. And then finally for your pole, it's going to be this diagonal line going here. Since we have the graph in front of us and we have the visual line of symmetry, we can quickly pick out which ones work and which ones don't work. So I can say for sure that theta equals pi over 2, our vertical line, doesn't work. There's no way to take my function and fold it over this vertical line and have it kind of line up. I can also say for the same reason that our pole doesn't work. Again, I can't fold my equation or my graph over this orange line and have it line up on itself. But I can for the polar axis. I can take this portion of the graph and fold it up and have it line up with this top portion. So for this specific limosome, we can say that it has polar axis symmetry. Looking here at rose curve, again, I've drawn our 3 axes of symmetry. We have our theta equals pi over 2, we have the polar axis, and then we also have the pole. Now this specific function actually has all three lines of symmetry. You can see I can definitely take my graph and fold it across the vertical line and have it line up on itself. I can also take it and fold it across our horizontal line and have it line up on itself. And then for the pole, again, I can do the same thing. Now this might not work for all rose curves. Again, it's based off of the number of petals you have, and that's based off of n being even or odd. It's also based off the orientation, which could be the sine versus the cosine function. But once you sketch the function and you draw your lines, you can see for this specific one that we have all three lines of symmetry. All right, for our last example here, we have lemniscat. Again, I've drawn in our three lines of symmetry. And then for this specific one, looking at our lines, I can say that we definitely don't have symmetry across the pole. So when I look at this diagonal line, I can't exactly fold it across that diagonal line and have it line up on top of each other. But it works for theta equals pi over 2, and it also would work for the polar axis, so this graph has two lines of symmetry. When finding your maximum values, it's always going to be equal to the absolute value of r, because we're looking for a distance here. In order to do this, we're going to have to use our memory of the unit circle. So to begin with, we have to remember, where does the cosine have a maximum value? And the cosine has a maximum value of 1 at the following angles of 0 and 2 pi. So if the function I'm dealing with has a positive cosine, then I would go ahead and plug in my values 0 and 2 pi. For the minimum, the cosine has a minimum value of -1 at pi. If we had a negative cosine, that would actually flip this minimum to make it a maximum. So again, I would be using pi if I had a negative cosine function. For my sine function, it has a maximum value of 1 at pi over 2. So if the function I'm dealing with has a positive sine function, I would be using the angle pi over 2 to help me identify my maximum. And then we can identify that sine has a minimum of -1 at the following angle of 3 pi over 2. And if I had a negative sine function, again, it would take that minimum and turn it into a maximum. So if the function I'm dealing with has a negative sine function, I would then use the angle 3 pi over 2 to help me identify my maximum. Let's go ahead and look at some examples and see how we can actually do this. All right, so for our first example, we want to find the maximum for 6 plus 12 cosine of theta. So going back to our last list, we want to look at, is it a positive or negative cosine? And in this case, it's a positive cosine. So a positive cosine is going to have a maximum at two different angles. It's going to happen at 0 and at 2 pi. So what this means is I'll have 2 points where I'll have a maximum value for this function. To find my actual maximum value, I'm going to plug in those values. So I have r is equal to 6 plus 12 cosine of 0. And then I also have r is equal to 6 plus 12 cosine of 2 pi. Again, we discussed the fact that a maximum value for the cosine was in fact 1. So I know that cosine of 0 is going to be 1, and cosine of 2 pi is going to be 1. So these both are going to simplify to be r is equal to 6 plus 12, or giving us a maximum value of 18. Which means that we're going to have a maximum value of 18 when theta is equal to 0 or when theta is equal to 2 pi. For our next example, we have a positive sine function. So we want to try and think about where the positive sine function has a maximum, and that's going to occur at pi over 2. But notice that we don't have a simple sine function, we have sine of 2 theta. So if I plug in pi over 2, this 2 would end up making that a pi value, and that wouldn't actually give me a maximum. So what I'm going to do instead is take this expression of 2 theta, and I'm going to set that equal to our initial angle of pi over 2, which is where we initially would have a maximum. And then by solving for theta, I can figure out what angle I actually need to plug in. So when I solve this expression for theta, I end up getting that theta is going to equal pi over 4. So when I now plug this pi over 4 into my function and multiply it by a 2, it gets turned into a pi over 2, and then I can help find my maximum. So I'm going to go ahead and do that. We can see that to find our maximum value, we have r is equal to 5 times the sine of 2 times pi over 4, which simplifies to be 5 sine of pi over 2. And I know that the maximum value for a sine function is 1, so I can say that this whole expression here is going to simplify to be just 1, which means that my r value is going to equal 5. So I have a maximum value for this function at the point 5 comma pi over 4. And for our final example here, we have r is equal to 3 minus 4 cosine of theta. Now for this function, we have a negative cosine. So in order to find the maximum, we're actually going to be considering the minimum, because that causes it to flip and become our maximum value. So I want to identify, where does the cosine have a minimum value, and that's going to happen at the angle pi. So to help me find my maximum, I'm going to plug in a pi for my cosine, which means I have 3 minus 4 times the cosine of pi. The cosine of pi is going to be a -1, and when I multiply that -1 by a -4, it's going to end up being a positive value, which is again how I find my maximum. So I now have r is equal to 3 minus a negative 4, which ends up being 7, which means that I have a maximum for this function at the point 7 comma pi. All right, guys, that does it for our notes. Go ahead and get started on the homework, and good luck.